Hi, everyone. This is online lecture number 6 for Philosophy 1600. I just want to quickly review what we did last week in the online lecture. We looked at some rules for calculating complex probabilities. We looked at two kinds of events. So let's just quickly go through the slides from last week. So we looked at first of all, we defined probability. We said the probability of events occurring is the number of favorable outcomes divided by the number of total possible outcomes, right? So as examples, um, the probability of getting tails on one toss of the coin is 1/2, right? 1 is the favorable event, and 2 is the total number of events. The probability of getting a 2 and rolling a die is 1/6. 1 is the favorable event, and 6 is the total number of events. The probability of getting a king drawing once from a deck of cards is 4/52. 4 is the number of favorable outcomes, and 52 are the number of possible outcomes. So that's called the frequency definition of probability. And we saw what a probability of 1 means the event is certain, a probability of 0 means the event is impossible. And typically in the real world, probabilities tend to be between 0 and 1, right? So you will never get a probability greater than 1 or less than 0. So we talked about complex events, and there are two kinds of complex events. There are conjunctive events, the probability of A and B both occurring. For example, getting snake eyes rolling 2 dice simultaneously, 1 and 1. That's a conjunctive event. A disjunctive event is the probability of getting A or B. So, for example, the probability of getting either a king or a queen drawing from a deck of cards, right? That's a disjunctive probability. And so we saw that there were rules for calculating both. For typically for for so-called conjunctive probabilities, you're going to use simple multiplication. So let's say, for example, you have two events. The probability of A and B will simply be the probability of A times the probability of B. Sorry. So what are the odds of getting snake eyes rolling 2 dice simultaneously? It'll be the probability of getting a 1 on the first dice times the probability of getting a 1 on the second dice, which is 1/6, times 1/6 equals 1/36. All right. Okay. Now things get a bit complicated though, because sometimes both events, or no, we'll just leave it at that for now. Okay. So anyway, that's a conjunctive event, but we're going to get a more complicated rule that's coming up a bit later on, and those will involve conditional probabilities. I didn't mean to jump the gun there. Sorry. So what are the odds of getting 2 kings in a row drawing twice from a deck of cards? Well, here's the thing. Now, this is where things get a little bit more complicated, because if I replace the card and reshuffle the deck so that it's re-randomized, then obviously the odds of getting 2 kings in a row will be 4/52 times 4/52. But as we saw, if you don't replace what you drew from the deck, then there's one less king in the deck and one less card. So then the probability of getting 2 kings in a row will be 4/52 times 3/51, right? So that's called a conditional probability. So basically the probability of A and B will equal the probability of A times the probability of B given A. That's called a conditional probability. That's when the events are when the events are dependent on one another. When they're independent, then you simply multiply, right? But if they're dependent on one another, then you have to take that into account with your second probability, right? So examples of independent events: getting snake eyes and rolling 2 die. Well, clearly, as long as the dice don't collide, the probability of the one is the same as the probability of the other, right? Again, I gave the example last week of buying lottery tickets. So I buy a lottery ticket this week, and I buy a lottery ticket for a separate draw next week, they have no effect on one another. Those are completely independent events, okay? But there are also events that are not independent. So I have at the bottom of this slide, getting 2 kings in a row, drawing twice from a deck of cards without replacement. I draw, let's say, and I get a king the first time. That's going to affect the probability of getting a king the second time, because there's one less card in the deck, so there are only 51 now, and there's one less king. So it will then be 4/52 times 3/51. And so that's a complication that you have to keep in mind for conjunctive probabilities. So we did some examples last week, all right, together. And so those are all on the slides here if you want to look those up. Okay, the next topic that we talked about last week was calculating the probability of a disjunctive event. And when you are calculating disjunctive events, you, instead of multiplying, you add, right? So let's say the probability of getting, I don't know, the probability of, let's say, getting um, uh, at least 1 6, rolling a pair of dice. Well, that's going to be 1 over 6 plus 1 over 6 equals 2 out of 6, right? Because what we're doing is we're adding the probabilities together. And of course, but then we also, as you saw, we have to subtract from that the chance of getting, let's say, the same thing on both dice. Then you have to subtract that, right? So when the events are, as it were, are mutually exclusive, you don't have to subtract. But when the events can both occur, then you have to subtract the probability of both happening. So if I say, okay, so let's say, for example, I'm drawing from a deck of cards, the probability, and I want to say, what is the probability of getting at least 1 king if I replace? Okay, well, in that case, it's okay, it's going to be 4 out of 52 plus 4 out of 52 minus 4 out of 52 squared. But what are the chances of getting a king if I don't replace? Well, that would be 4 out of 52 plus 4 out of 52 minus 4 out of 52 times 3 out of 51, right? So, but the thing to note about disjunctive events is that the probabilities are added instead of multiplied. Now, if the events are mutually exclusive, then you just add the events and that's the end of it, right? So, for example, the probability of getting a king or a queen from one draw of a deck of cards, those you can't get both, right? If you just draw one card, you're going to get one or the other. So therefore, the probability would be 4 out of 52 plus 4 out of 52, period, right? Because the two events are mutually exclusive. You can't get both. Now, if I say the chance of getting at least 1 king, of getting at least 1 king, well, that's a little bit different because not only could I get a king on the first or a king on the second, but I could also get 2 kings in a row. So then it would be 4 out of 52 plus 4 out of 52 minus 4 out of 52 times 3 out of 51, right? Okay, so that's basically what we did last week, and I went through a lot of examples with you. And if you want to go through the examples again, those are on both the PowerPoint slides, and that's also on online lecture number 5. All right. So I just wanted to recap with you what we did last week before we move on to the next online lecture. Okay. So that's just a review from last week. So I'm going to now upload the PowerPoint for this week's lecture. So just give me a second here. I apologize. Okay, so we'll stop sharing that one. And then I'm going to share now the PowerPoint for this week's lecture. Okay, so let's see, where the heck is it? Okay, probability 2. So that's what we're going to do this week. There it is. Okay, all right. So anyway, so so the assignment that I posted today, actually, for Thursday, that's due in the lab on Thursday, that assignment is based on last week's online lecture. Okay, we're going to look at some complications today, but that won't be on the upcoming assignment. You'll only be looking at problems from last week's lecture. All right. Now, I will tell you that some of this material could find its way onto the midterm, but I have suggested exercises based on this lecture, right, that you will go over with your GA in lab. So even though you won't be doing an assignment on what we're talking about today, you will work through exercises with your GA in the lab so that you be in good shape for the upcoming midterm. All right. So I should tell you, actually, so the midterm then is scheduled for, I'm going to post it Thursday night after all the labs have been done, right? Including, there are a couple labs that are 7 o'clock. So maybe around 8 or 9 o'clock, I'll post the midterm, and then it'll be online. That'll be February 27th, and I'll make it due March the 2nd. How's that? So that's, I believe, a Sunday evening. So you have 2 or 3 days to work on it. Lots of time. You can use your lecture notes. You can use your assignments, whatever you want, right? It's an open book test so you do that, on your own. It's not timed or anything like that. And then once you're done, you submit your test as a Word document online, and then the GAs will grade your online submission, okay? So that's coming up on the 27th, and it will cover the first half of the course, all right? Also, too, to let you know, there will be no online lecture, obviously, next Sunday, because that's the beginning of the midwinter break, right? So there'll be no lecture next Sunday. And I don't plan on having a lecture the following week because there will be no new material covered that week. What I will do is that the week before the midterm, I'll post a practice midterm. And then you will go through that with your TA, or rather your GA in the lab, uh, the following week. And then once you've gone over that, so that'll be what, on the 27th. So you'll go over that with the GA that week, the practice exam, okay? And then that evening I will post the actual exam. All right. So you'll be very prepared and in very good shape to do the online exam that will be posted on the 27th. Okay. All right. So the other topic I want to cover this week is the complementation rule. And this allows you to do slightly more complex calculations when you have three conjunctive or disjunctive events, right? So last week we primarily focused on just when you have just two events, right? But this week we're going to complicate things a little bit and look at when you have conjunctive events that consist of three conjuncts, or disjunctive events that consist of three disjuncts, all right? So as I say on the slide here, when we add the probabilities of all the event types in the event space, these probabilities sum to 1, right? So we know that. So basically, if let's say the probability of getting whatever it is, like the probability of drawing a red, well, that will then be 1 will equal the probability of drawing a red plus the probability of drawing a non-red, right? And that probability together will equal 1. All right. So here's an example. An urn contains 3 red balls and 2 green balls. The probability of drawing a red is, of course, 3 out of 5. The probability of drawing a green is 2 out of 5. Notice that equals 1. That's called the complementation rule. Okay, now again, consider an event A and consider all events that are non-A. By the way, just for, I hope you don't mind the technical term, but if I have an event A, like for example, getting a 3 or getting a red ball, let's say drawing from an urn, the complement class is just not A, right? So if A is an event, whatever it is, the complement class is anything that is outside of that event, right? So basically, the probability of A plus the probability of its complement will equal 1. So the probability of, let's say, getting a 1, rolling a dice, and the probability of not getting a 1 will equal 1. So for example, in the case of a dice, if I roll it once, my chance of getting a 1 will be 1 out of 6. And my chance of getting a non-1 will be 5 out of 6. So 1 out of 6 plus 5 out of 6 equals 1. So by doing a little bit of algebraic manipulation, the probability of A will then equal 1 minus the probability of not A, right? So again, if the probability of A and the probability of not A equal 1, the event and its complement, then clearly the probability of the event will simply be 1 minus the probability of its complement, right? That's just doing a little bit of algebraic manipulation. So as I say here, some examples will help to make the complementation rule a bit more clear, right? So the probability of getting ahead on one toss of the coin, as you know, all right, it's going to be 1. That, remember, we're using the complementation rule, right? It's going to be 1 minus the probability of tails, that is non-heads, equals 1 minus the probability of 1/2 equals 1/2, all right? Okay. The probability of getting a 6, rolling a dice once, it's going to be 1 minus the probability of getting no 6s, right? Which is 1 minus 5 over 6 equals 1 over 6. And as you know, that is the probability of getting a 6 rolling a dice once. The probability of getting a king on one draw from a deck of cards is, of course, 1 minus the probability of the complement class, which is getting no kings, which will be 1 minus 4 out of 50, 48 out of 52, right? There are 4 kings in the deck, and the other cards are non-kings, equals 4 out of 52. The probability of getting a red ball from an urn containing 3 red balls and 2 green balls is 1 minus the probability of getting is 1 minus the probability of getting a non-red, that is a green, is 1 minus 2 over 5 equals 3 over 5. So basically, the complementation rule sometimes makes calculations a little easier, right? As I say here, it comes in handy, pardon me, when you need to calculate the probability of disjunctive events whose complements are not mutually exclusive, right? As I say here, it obviates the need to use the general addition rule. So instead of using the addition rule, you can use the complementation rule, right? It's an alternative way of calculating disjunctive events. So as I say here, returning to the EARN problems from the previous lecture, the slides that we just looked at, right? You can use the complementation rule instead of the addition rule. So look, again, suppose there is an urn containing 3 red balls and 2 green balls. What is the probability of getting at least 1 red ball on 2 consecutive draws with replacement, right? So I draw a ball from the urn, then I add it back and I re-randomize and I draw a second ball, okay? So what are the chances then of getting at least 1 red ball on 2 consecutive draws for replacement? Well, again, using the complementation rule, the probability of getting at least 1 red is the probability of getting 1 minus the probability of getting no reds. In other words, no reds is the complement of getting at least 1 red. So it would be 1 minus the probability of no reds, right? And on the first and no reds on the second equals 1 minus 2 over 5 times 2 over 5 equals 21 over 25. So that's the chances of getting at least 1 red using the complementation rule. It's 1 minus the chances of getting no reds. In other words, not getting a red in the first draw and not getting a red in the second draw, which will be what? Well, there are 2 green balls, so that'll be 2 out of 5 times 2 out of 5, and we're replacing it, equals 1 minus 4 out of 5 equals 21 out of 25, okay? Or what, 84%. Now, what's important to note is you can get the same result using the general addition rule, okay? And so here it is on the next slide. It's a little more cumbersome. So again, the probability of getting at least 1 red is the probability of getting a red on the first, which is what? 3 out of 5, plus the probability of getting a red on the second, which is 3 out of 5. Okay, now if you don't subtract, then you're going to be in trouble because you're going to get 6 over 5. And as we know, 6 over 5 is not a meaningful probability. But what you're also going to do is subtract the chances of getting red on both draws. Well, if there's replacement, then it'll be obviously 3 out of 5 times 3 out of 5, which is 9 out of 25. So it'll be 6 out of 5 minus 9 out of 25. That is 30 out of 25 minus 9 out of 25 equals 21 over 25. So notice then that you get exactly the same results using the addition rule that you did using the complementation rule. So you can use both. It doesn't matter to me on the assignment. You can use one or the other. If it's just 2 events, you can use either the complementation rule or you can use the addition rule. They're both about this. You'll get the same results using both. All right. So now let's look at another one. What are the odds of getting at least 1 red ball if there's no replacement? Well, you know that's going to change things a little bit because the second time I draw, there's going to be one less red ball and 1 less ball in the urn. So then using the complementation rule, the probability of getting at least 1 red will be 1 minus. Okay, now notice here, instead of 2 over 5 times 2 over 5, I have 2 over 5 times 1 over 5. And the reason is that the second time I draw a red, if there's no replacement, there's 1 less red ball in the urn and there's 1 less ball in the urn. So it's going to be 1 over 4. And that will be 18 out of 20, all right, versus 21 out of 25, okay? But of course, again, you get exactly the same results using the general addition rule. So I have it here for you on the slide, right? The probability of getting at least 1 red is the probability of getting a red on the first draw, which is, again, 3 out of 5, plus the probability of getting a red in the second draw, which is 3 out of 5, which adds up to 6 over 5, minus the chance of getting red on both. Well, it's a little bit different this time because now the probability of getting a red on both will be 3 out of 5 times 2 over 4 because there's 1 less red ball in the urn and one less ball in the urn. And so it'll be 6 out of 5 minus 6 over 20. If I did the calculations correctly, that should give us 18 out of 20. So notice then that we get the same result using the addition rule that we do using the complementation rule. So you can use either one, especially when you're calculating the probability of two events. You can use either the complementation rule or you can use the addition rule, right? Either one will give you exactly the same results. Okay. Just a footnote here. It's not important for our purposes, but I say here, you can use complementation for getting conjunctive events, but it's unnecessarily complicated. So with conjunctive events, just stick to multiplication and conditional probabilities. But for disjunctive events, as we'll see shortly, the complementation rule can come in very handy when you have 3 or more events. Then it gets pretty messy if you don't have complementation. So as I say here, extending the addition of multiplication rules to complex events, right? Where you have 3 component events. Now things get a little more complicated, right? It's not, I mean, it's still okay, but so here's an example. Suppose I roll 3 dice. Let's say simultaneously, they don't collide, and I want to know the probability of getting 3 ones. All right, I don't know what you'd call that. 2 ones are snake eyes. I don't know what you'd call 3 ones. But of course, as you know, the probability is going to be pretty low, right? So there, you're going to use the simple multiplication rule. It's going to be 1 over 6. That's a chance of getting a 1 the first time, times 1 over 6, a chance of getting a 1 the second time, times 1 over 6, a chance of getting a 1 the third time. That will be 1 over 216. So the chances then of getting 3 ones is very slight. It's 1 over 216, right? And notice that we don't use conditional probabilities because these events are completely, assuming the dice don't collide, the events are completely independent of one another, right? So it'll be 1 over 6 cubed equals 1 over 216. Okay, let's look at the card example. What are the odds of getting 3 kings in a row from 3 draws from a deck of cards with replacement? Well, again, because there's replacement, we're not going to be using conditional probabilities because the events are independent of one another. So the probability of getting all kings will simply be 4 out of 52 cubed, right? 4 out of 52 times 4 out of 52 times 4 out of 52, all right? So generalizing, if A, B, and C are mutually independent events, then the probability of A and B and C will simply be the probability of A times the probability of B times the probability of C. Now, things get a little more complicated. If they're not independent, then we have to factor in conditional probabilities, right? And so we're going to have to use what I called in previous slides, the general multiplication rule. So see that coming up in the next slide. Suppose I draw 3 times from a deck of cards, but this time without replacement, okay? All right, well, let's see what happens. What are the odds that I will get 3 kings in a row? Well, again, remember that each time you draw, there's 1 less card in the deck and 1 less king in the deck. So the probability of getting 3 kings in a row will be 4 out of 52 times 3 out of 51 times 2 out of 50. Okay? So generalizing, we can say that when A, B, and C are not independent, we'll use a more complicated version of the multiplication rule. The probability of A and B and C when the events are not independent of one another will be the probability of A times the probability of B given A, and the third event, the probability of C given that A and B both occurred, right? Okay, so that's why if you look back up there for the chance of getting all kings, it's 4 out of 52. That's the probability of getting A. 3 out of 51, the probability of getting B given A, times 2 out of 50, the probability of getting C given A and B, right? So what are the odds then of getting all green balls by draw from the urn 3 times without replacement? All right. It's going to be, and then so it's going to be, if there are 10 balls in the urn and there are only 3 balls, to get 3 balls in a row, it's going to be 3 out of 10, right? Probability of A times probability of B getting given A, that'll be 2 out of 5. 1 less green ball in the urn and 1 less ball. And the next time, there will be, again, one less green ball and one less ball in the urn, so times 1/8. So as I say here, in a similar manner, we can extend the addition rule to just disjunctive events with 3-component events. What are the odds? So I get either a 3 or a 4 or a 6 rolling a die once. Very straightforward. You just add it up, right? So it'll be 1/6, which is the odds of getting 3, plus 1/6, which is the odds of getting 4, plus 1/6, which is the odds of getting a 6, equals 3 out of 6. That is 1/2. All right. So again, it's just like with the multiplication rule, right? You're multiplying 3 events. Here you're adding 3 events for the disjunctive event. Okay. So that's not super complicated. So again, the probability of getting 3 or 4 or 6 will be the probability of getting 3 plus the probability of getting 4 plus the probability of getting 6 equals 3 times 1/6 equals 3/6 or 1/2. So far, so good, right? What are the odds that I will get a king or a queen or a jack drawing once from a deck of cards? Well, again, pretty straightforward because those events are mutually exclusive, right? You can only get one or the other, all right? So then it's going to be, you just add up 4 out of 52 plus 4 out of 52 plus 4 out of 52 equals 12 out of 52. Okay, pretty straightforward, right? And the events are independent, so you just add them up. Generalizing then, when events A, B, and C are mutually exclusive, when you can't get both of them or all of them, then the probability of A or B or C is simply the probability of A plus the probability of B plus the probability of C. Here's where things get more complicated, right? What if A, B, and C are not mutually exclusive? Then it gets more complicated. So I'm going to tell you right now, I didn't put it on the slide, but if you want to calculate the probability of getting getting at least one king on 3 draws of a deck of cards when you don't replace, it gets really complicated. And so I don't see any point in putting the formula on the slide. It's like the formula itself will take up half the slide, right? So instead, when we have 3 events that are not mutually exclusive, then instead of using addition, we use the complementation rule. That's your best bet. Okay. So again, what are the odds that I will get at least one king on 3 draws from a deck of cards with replacement? Okay. Well, again, that's not a big deal, right? You just add it all up. But I can also, but okay, let's say with replacement. Sorry, I kind of jumped ahead of myself. Even if it's with replacement, you can also use complementation. My apologies. So I could either add them up like PA plus PB plus BC, or I could use complementation, which is 1 minus the probability of getting none of them, right? That's a complement class. So the probability of A or B or C equals 1 minus the probability of getting not A and not B and not C. So the probability of getting at least one king, if I replace, will be 1 minus the probability of getting no king on the first or on the second or on the third, which will be 1 minus 48 out of 52 cubed, all right? But here's where it gets complicated. I'm sorry for jumping ahead there. If there is no replacement, then you have to basically use a complementation. Believe me, don't try. If you use the addition rule, it gets really complicated, and the formula is really complicated, and that's not something I want to test you on or that I expect you to know. So here, the probability of getting at least one king is simply, okay, using complementation, it's 1 minus the probability of getting no kings, right? Okay, so look at this. Look at the formula here. It's 1 minus the chance of getting no kings on the first draw is 48 out of 52. If there's no replacement, then there's one less king in the deck and one less card in the deck. So the chances the second time of getting no kings are 37 over 51, right? And the third time, there's one less non-king still and one less card. So now it's going to be 46 over 50. So the probability of getting at least one king will be 1 minus 48 out of 52 times 47 out of 51 times 46 out of 50. All right. So again, we're using the complementation rule. Now, for the example where you do replace, you could use either the complementation or the addition. They're both equally expedient. But believe me, when there is no replacement and the events are dependent on one another, then you have to use complementation, because otherwise the calculations become unnecessarily complicated. Okay. So let's just do a little bit of a review together. All right. So to recap, and by the way, because it's an online test, you realize you don't have to memorize these formulas, right? But you should know them like the back of your hand if you do enough problems. But you don't have to memorize them. This is not a memory test, okay? A reasoning skills test is not a memory test. I'm trying to test your ability to think critically, to think logically, right? I'm not testing how good your memory is. So anyway, but anyway, let's go over these formulas. So to recap, these are the probability rules that we have learned in the in not the last two lectures in, well, yeah, actually this lecture too. Okay, so here it is. First of all, we have on top what is called the complementation rule. The probability of A is equal to 1 minus the probability of its complement, right? That's what we just talked about. The probability of A and B, just multiply, right? The probability of A times the probability of B. If the events are independent, right, then you don't need to use conditional probabilities. If the events are dependent, then you need to use conditional probabilities. So then the probability of A and B will be the probability of A times the probability of B given A. All right, that's when A and B are not independent. Okay, so that's for calculating conjunctions. And again, on top, we have the complementation rule that we just learned in this lecture. Okay, now let's look below for the disjunctive event. The probability of getting A or B is the probability of A plus the probability of B, and that's it. If the events are mutually exclusive, all right? So again, drawing from a deck of cards, just once. The probability of getting a king or a queen will be the probability of getting a king and the probability of getting a queen. I can't get both if I just draw one card. So then it will be 4 out of 52 plus 4 out of 52 equals 8 out of 52, right? Okay, that's for disjunctive events that are mutually exclusive. However, if they're not mutually exclusive, then what you have to do, as we've seen, is you have to subtract the probability, right? You have to subtract the probability of getting both events. So again, the probability of A or B will be the probability of A plus the probability of B minus the conjoint probability of getting A and B if A, B are not mutually exclusive. Okay. Now, what we've learned today is using the complementation rule in part, how to extend these rules to complex events that have 3 components. All right. So again, the probability of A and B and C, really it's just an extension, right? It's just the probability of A times the probability of B times the probability of B, assuming that A, B, and C are independent, right? It's that simple. Okay. It really, it's that simple. So that's probability. So again, the probability of getting, let's say, a king 3 times in a row with replacement will be 4 to 52 times 4 to 52 times 4 to 52. It's that simple, right? However, if the events are not independent, let's say B depends on A and C depends on B, then things get a little more complicated, but you're still just multiplying. So the probability of A and B and C will be the probability of A times the probability of B given A times the probability of C given A and B. That's if B, A, and C are not independent. All right. So the probability of getting a king 3 times in a row, if I don't replace, will be 4 out of 52, right? Times the second time there's one less king and one less card, times 3 out of 51. And then the third time there's one less king and one less card, times 2 out of 50, right? So you have to take into account conditional probabilities when you're calculating the probabilities of conjunctive events with 3. Well, just like you did with 2. Okay. Now, when you have a disjunctive event with 3 components, you don't use addition. In other words, don't go there, okay? Take my advice. Instead, what you're going to use for that is complementation. Now, there is an exception. If the events are mutually exclusive, then you can just add them up. Then you don't have to use complementation, right? You can if you want, as we saw on the previous slide, but you don't have to. Okay, so for example, again, the chances of getting a king or a queen or a jack on one draw from a deck of cards will be 4 out of 52 plus 4 out of 52 times 4 out of 52 will be, what is that, 8, 12 out of 52. That's all you got. So you can use computation, or you could say the chance of getting at least one king, all right, would be minus the probability of getting no kings. So it'll be 1 minus 48 out of 52, right, times 48 out of 52 times 48 out of 52 would give you the same result that you would using the addition rule. However, where you absolutely have to use complementation for a disjunctive event where there are three components is when the events are not mutually exclusive. Then you have to use complementation, right? So if I have the probability of A or B or C equals, B or C, if the events are not mutually exclusive, then it's going to be 1 minus the probability of none of them, right? So the probability of getting at least one king will be 1 minus the probability of getting no kings, right, on the first, and the probability and getting no kings on the second and no kings on the third. Okay, so what you have to do then is to subtract from that the complement class. And if the events are independent, then it'll just be not A and not B and not C. If they're dependent, it'll be not A, it'll be not B given not A, and it'll be not C given not B and not A. Okay, so anyway, those are the rules for calculating probabilities, and these are all the rules you will have to use, you'll need to use on the midterm, all right, and that is coming up in a couple of weeks, right? So you'll need to know these rules. You don't have to memorize them. Remember, it's an online test, but you should really know them like the back of your hand, right? You don't want to spend too much time running the online test. So you should know these, as I say, like the back of your hand, okay? So why don't we try some additional problems, right, for practice? Practice makes perfect. And this, again, will help you with the suggested exercise you do in the lab next week with your GA, and it will help you on the midterm, all right? So here are some additional problems. One, what are the odds of getting either a king or a queen on both draws, right, from a deck of cards with replacement? Okay, well, that's pretty straightforward. It'll be 8 out of 52 times 8 out of 52, right? The chance of getting a king or queen on the first draw is 8 out of 52. On the second one, it's 8 out of 52. If you replace, then it's just going to be 8 out of 52 times 8 out of 52. What are the odds of getting a total of 10 rolling a pair of dice? All right, well, altogether, there are three options, so it's going to be 3 out of 36. All right, now we get to slightly more complicated problems. What are the odds of getting a total of six rolling 3 dice simultaneously, right? So now it's not 2, but 3. So let's say, you're at the casino, you roll 3 dice, right? And you want to know the probability of getting a total of 6. Well, what you do is you think about all the different possibilities, right? First of all, you could get, okay, so sorry about that. The calculations aren't very good there. So let's say getting a total of 6, it's going to be more complicated. It's going to be, let's say what, 2, 2, and 2 is one possibility. By the way, I'll correct this slide. Okay, well, after the online lecture, I'll correct the slide. What it should be is the probability of getting, let's say, 2 and 2 and 2, or the probability of getting, 1 and 4 and 1, or the probability of getting, I don't know, 2 and, getting 3 and, let's say, 1 and 1 and so on. Well, I'll tell you what I'll just redo that particular problem. Sorry about that. Number 4, what are the odds of getting, but anyway, yeah, so anyway, so you're going to get 2, 2, 2, and you're going to get 1, 2, 3, and there are 6 ways of getting that. And then you're going to get, and I think that's about it, right? So altogether, I think it's 7 out of 36. 7 out of 216. I'll calculate that. I'll redo this slide, okay? So just rest at ease. I will redo slide number 10. What are the odds of getting at least one ace from a deck of cards 3 times with replacement, okay? So remember that we're going to use the complementation rule. So the probability of getting at least one ace will be 1 minus no aces, right? That's the complementation rule. Well, the chance of getting no aces are what? 48 out of 52 cubed, right? Where there is replacement. So it'd be 1 minus 48 out of 52 cubed, and that will be the probability of getting at least one ace. What are the odds of getting at least one ace drawing from a deck of cards 3 times without replacement? Okay, so it's going to be a little bit different this time. We're still going to use complementation because remember, for disjunctive events with 3 components, you should use you should still use complementation, all right? So the probability of getting at least one ace will equal 1 minus the probability of getting no aces equals 1 minus 48 out of 52 times 47 out of 51 times 46 out of 50, okay? Notice that this time, the events are dependent on one another. So the first time I draw, the chance of getting no aces, remember I'm using complementation rule, it's 48 out of 52. But the second time I draw, there's one less non-ace and one less card in the deck, so it's going to be 47 out of 51. And the third time I draw, it's going to be 46 over 50. Okay, so therefore, so do you see then the difference between number 5 and number 4? Okay, number 5 and number 4. In number 4, I just do 48 over 52 cubed because remember, I'm replacing each time and re-randomizing. So there's replacement, and so you don't use conditional probabilities in the complement class, right? But when you don't replace, then you have to use conditional probabilities in calculating the complement class, right? Okay, number 6. Suppose an urn okay, right. So suppose an urn contains 4 red balls, 3 blue balls, and 3 green balls. What are the odds of getting exactly 1 red ball if I draw from the urn twice without replacement? Okay, well, in this case, if it's just twice, the probability of getting exactly 1 red will be as follows. It'll be 4 over 10 times 6 over 9 plus 6 over 10 times 4 over 9. Why? Okay, well, again, I want to know the probability of getting exactly 1 red without replacement. So look at the first time. So the first time, it's 4 out of 10, right? Because there are 4 red balls and 10 balls in the urn. But the second time that I draw, because there's no replacement, there will be 1 less ball in the urn. So it'll be 6 over 9. All right. And the same thing with the second time around. So there are 2 possibilities. I get a red the first time and a non-red the second time, or I get a non-red the first time and I get a red the second time. That would be exactly 1 red ball. Okay. So in that case, it's 4 over 10 times 6 out of 9 plus 6 over 10 times 4 out of 9 equals 48 out of 90. So that's the probability of getting exactly 1 red. Okay. So these will help you to work through the suggested exercises with your GA next time. And as I say, I will make corrections to number 3. Okay, so I'll post that after I post this lecture. So look at the revised slide and you'll get the correction to number 3. Otherwise, everything's good. All right. So again, what is the goal? So the goal by the end of this lecture is that you know how to do calculations of probabilities for disjunctive and conjunctive events, either where the event, or so for conjunctive events where the events are independent or they're not independent, right? And for disjunctive events where they're mutually exclusive or they're not mutually exclusive. All right. Then we learn how to extend the rules for 3 component events. So for a conjunctive event, it's very simple. You just multiply 3 times. So the probability of getting 3 kings in a row, drawing 3 times from a deck of cards will be, again, 4 out of 52 times 4 out of 52 times 4 out of 52 if there is replacement, right? If there is no replacement, then it'll be 4 out of 52 times 3 out of 51 times 2 out of 50, all right? But basically, for 3 events, it's just you just multiply. It's very straightforward, right? And if the events are not independent, then you use conditional probabilities. But it's pretty straightforward. And for disjunctive events, again, it's pretty straightforward. You just add up the events, right? If they're mutually exclusive, it's very simple. So the chances of, let's say, getting I don't know, a king, let's say, or a queen or a jack, drawing once from a deck of cards again. That's going to be 4 out of 52 plus 4 out of 52 plus 4 out of 52 will be 12 out of 52. And because they're mutually exclusive, I don't need this. So that's very simple. So when the events are not mutually exclusive, you can use the addition rule. You can also, if you want, use the complementation rule. So again, the example I just gave you, the chance of getting, so let's say the chances of getting a king or a queen or a jack or whatever, you can use complementation. It'll be 1 minus the probability of getting none of them, right? So it'll be 1 minus, and then again, if there's replacement, so it'll be 1 minus. So what is 12 minus 52? So it'll be 40 over 52 times 40 out of 52 times 40 out of 52. If there's no replacement, there'll be 40 out of 52 times 39 out of 52 times 38 out of 52, right? Or sorry, 40 out of 52 times 39 out of 51 times 38 out of 50. All right. So anyway, the rules are very straightforward. Again, if you go back to this slide here, slide number 9, I have all the rules listed. All right. So they're all listed for you. And these are the rules that you use. Okay. These are the rules that you use for calculating probabilities. So using those rules on slide number 9, you can calculate anything I throw at you on the midterm, right? Without any problem whatsoever. Just apply the rules, right? Again, you'll be going, you have your assignment that you're doing, and you have your suggested exercise that you go through with your GA. So by the end of this coming week, you'll be in good shape to do any problems I throw at you in terms of probability on the midterm. All right. Okay. So look, so this will be the last lecture for a couple of weeks. Have a good break, and good luck on the midterm. As I say, I will post a practice midterm you will go over with your GAs in the lab before I post the midterm. So that way you'll be in really good shape to do the midterm. Okay. So my apologies for that glitch on that one slide, but otherwise I think we covered everything pretty well this evening. Have a great week and have an excellent break.